Question?
Can you explain like the SO2 structure and polarity?
The what, the what?
SO2.
Oh, I thought you said SN2. I'm
No,
like, we don't cover SN2 until test 3. Okay, let's look at that. That's where we're picking up at. Any questions about lab today?
I have a question about what we did yesterday.
In lab?
No, not in the lab,
Okay, go ahead.
but, with the, electron geometry, the, lone pairs that are in p orbitals, do those contribute to the electron geometry, or no? Because if it's like an sp2 hybrid, I generally would think that it's definitely being trigonal planar.
SP2 would be SP2 would be trigonal planar.
Even if it has a lone pair.
The lone pair would make it the 4th region,
Right.
but no, it's not going to be tetrahedral. So in the end, the answer is no. Only the hybrids contribute to the geometry. SP2 is going to always be trigonal planar. The lone pair will be the 4th region, but we don't make it SP3. The lone pair instead is in that p orbital that we get by being SP2. SP2 is always trigonal planar. The lone pair is here where the trigonal planar is, I have boom, 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 here, boom. Okay. And the p orbital is perpendicular to that lone pair, most likely because there's a p orbital next door and they can interact. Any questions about lab today or tomorrow? Yes?
In the video, it was talking about the sodium hydroxide, and it says 1N.
Uh-huh.
Was
Uh-huh. Normality, you learned normality in Gen Chem? Well, you need to look up normality. Normality. Here you can find it on Wikipedia or anywhere. Very important. It's alternative to molarity. Uh-huh.
Do the students who have lab exempted, do they still need to do the lab assignment you sent in the email yesterday?
No, that is a lab assignment.
Okay.
Just that's lab. So no. If you're not taking the lab though, there occasionally when we will have lab lecture downstairs, you need to attend that. That is lecture that we're just doing during lab period. But not the assignment. If you're not getting emails, please let me know. A couple of you have contacted me. For example, yesterday I sent out this handout. This handout here. Which includes the nomenclature portion, which is covered by video only. Okay? And I also sent out the literature assignment, the lab literature assignment that is going to be done instead of lab on Monday, Tuesday, because we won't have lab on Monday, Tuesday because of Memorial Day. We'll be here on Tuesday, but since we're not here on Monday, we're not going to do lab on Tuesday either because it's a repeat. Monday and Tuesday. So lab the literature assignment instead, and that is due when you come to lab on Wednesday, Thursday, as I said in the email. I think that's good. We can confirm that in a couple of days if we need to. So that should be clear from that email I sent. Okay, polarity of these. Water is a polar molecule, mainly because it is bed-shaped from the fact that it's tetrahedral. The dipoles do not cancel. What about these other guys? CO2. We need Lewis structure. If you do Lewis structure, you're going to end up with CO2. Well, the carbon's actually in the middle. CO2, typically, carbon's in the middle and then the oxygen's here. I'm not going to do systematic, but you can get to this here. You could also put together a structure like this for CO2. I don't know if that exists. If it does, it ain't the CO2 that we exhale. Okay, this is the CO2, and you end up with double bond here, lone pair here, lone pair here. You can get to that systematic approach. Every atom has standard bonding. And what type of geometry do we expect? Is this correct? Is it indeed linear? What do we expect of that carbon geometry? Why linear? Further explain. Why?
Oh, yeah,
It's sp. How many regions are on this carbon? 2. Okay. It's sp. Could you graph the hybridization of that carbon? Right? It's sp, which is 2 hybrids, 2 p orbitals left over. What type of bonds do you see the carbon making?
Double.
Sigma bond to oxygen, sigma bond to oxygen. Pi bond to oxygen, pi bond to oxygen. Okay? Using these orbitals. How many p orbitals does this central carbon contain? 2. Right? Okay? What are their positioning to each other? All your p orbitals, as you learned in Gen Chem, are all orthogonal to each other, 90-degree angles. Boom, here's 2 of them, the other one is coming out like this. Okay? Right? If you got 2, they're 90 degrees. These 2 p orbitals are like this, over interacting. These 2 are like this, interacting this way. This carbon has 2 p orbitals, like that. One of them is interacting with that oxygen p orbital like this, and it is like this. And then here you got these 2. Okay, 2 here, and it's like that. The one in the middle has 2, one up and one perpendicular to it. Okay, that's structure. Anytime you look at molecules, you need to think about it. Okay, what's going on here? And test yourself and ask questions about it. And say, yeah, okay, I understand. Maybe I don't know. Well, I'll ask. So, it is SP, it is drawn right, it is linear, and okay, linear through here, because the hybrids set your geometry. All right, these 2 set the geometry, and these are going to be spread out linear. All right, that's a little review. So what do we got here? We got carbon to oxygen is pulling, and this one is also pulling. Are those equal and opposite? Yes, same intensity because it's O and O, and they're exactly opposite. So those vectors cancel, and there's no net dipole. You can only see the result, the net. We don't really see it, we see the consequences of it. For example, if you put CO2 in an electric field, it's not going to respond because there's no polarity. What does polarity mean? Do you know what polarity means? An uneven distribution of electron and thus charge. Okay? It's not polar. It doesn't have an unequal distribution. You've got to understand that. Non-polar. CO2 is non-polar. SO2. Well, SO2, by the way, how many valence electrons were here? We got them up there. We could count them. How many valence electrons here? 18? Yes, let's make sure we have 18. Typically sulfur in the middle here. I think you learned in Gen Chem that the least electronegative atom in the middle. Is that what you learned? You learn something like that when you polyatomics? That's not always, but that's just kind of a starting recommendation. Okay, let's bond this to each oxygen. At least once, right? I mean, it's got to be at least single bonded to the oxygen. SO2, that's it. How many? 18. Okay. What do you want to do next? Put electrons. Let's make oxygen happy. Now it has an octet. 2, 4, 6, 8, 10, 12, 14, 16. We need to put one more lone pair up there. Where do you want to put it? It has to be on sulfur because we can't put any more around oxygen. Put it on sulfur. There you go. Are we done? Are you happy with this structure? No. Why not? Does everything have an octet? No. Sulfur does not have an octet. How many does it have? 2, 4, 6. What are we going to do? We can't put another lone pair up there. We're going to have to ask the oxygen to share, right? these electrons move in. What does this arrow mean?
Making a bond.
These electrons are falling in and making a 2-electron covalent bond. Okay? Now we're actually doing resonance. Double-headed resonance arrow. Now we have S double bonded to O, 2 lone pairs instead of 3. And this over here is still 3. That arrow leads us to this, nothing else. Everything has to come from your arrow movement. Don't forget the lone pair here, it's still there. Okay, so for good now? 2, 4, 6, 8. Yes, 2, 4, 6, 8. Huh. It's got an octet. This is typical structure here. Charge. There's charges here. I'm not going to deal with that. Let's deal with this though. Charge. Charge of this oxygen. Neutral. Sulfur.
Isn't it +1 because sulfur can make 5 bonds?
I mean, does it own? It owns one of each bond. 1, 2, 3, 4, 5. It owns 5. It's supposed to own 6. It's missing 1. Positive charge. Charge of oxygen? Negative. What's the net charge of this molecule? Neutral. Neutral. If it wasn't neutral, I should have shown a charge right here. Is it neutral? Net neutral. Okay. You can look at the charges there on your own. They're more than plus or minus. 2 plus or something probably. 2 minus. Is this a good structure?
No.
Why don't you like this structure?
You can make another double bond with the oxygen to where there's no, to where the whole thing is neutral.
Okay. You want to take these and move them in here and get double bond there, double bond here,
And then a lone pair.
and then still lone pair there. We've never done anything with that lone pair, right? You like this structure better. But hold on. Sulfur now has 2, 4, 6, 8, 10 electrons around
It can. It has an expanded
it.
oxygen.
It actually can, yes. But some people don't like to expand octets even when you can. Some people actually prefer this structure. And not that your preference matters in the chemistry world. What I mean is by you make a better argument for this structure. No charges here. Because if you want to stick to octets, then this is your better structure. What's the likelihood of this oxygen sort of sharing these electrons with sulfur like this? Oxygen's more electronegative, very greedy, wants to hold on to them. Maybe oxygen likes to be negative. What's your argument for this?
I just like it because it doesn't have areas of partial charge. The whole thing is completely neutral.
Well, these are not partial charges, these are actually formal charges.
Cool.
A partial would be a partial, and these are formal charges. No charge. No charge separation.
Right.
Okay, that's a reasonable argument. We can make arguments for both. Should be able to make arguments for both. Okay, these are actually resonance structures. We don't have to decide. The true structure is actually somewhere in between these. That is, this is sort of trying to make some bonding in here. Is it a full bond? No. No. We got a single bond, okay? And I have some electrons. I'm oxygen, and you're positive. Is the electrons in the oxygen going to be attracted to the positive sulfur? That's physics. Minus attracted to positive. Okay? I got electrons. They're going to be somewhat attracted here. All right? But is it going to be a full bond? Are we going to come in here bond?
Sometimes.
I don't want to give up my electrons. So let's make a peaky bond. So it's a full bond and maybe some partial bond here. Maybe this is just a partial bond. Well, again, it's somewhere in between. That's resonance. Guess what? Resonance covered there in test 3. But along the way, we always mention resonance. You read about it. It's usually in textbooks in chapter 1, chapter 2, including the Klein book. I don't like to cover all the resonance that early because I don't think you're ready for it. We'll learn a little bit as we go along. Okay? Resonance. Resonance is when one absolute structure isn't adequate to tell the full story. It's a lot like colors. What is pink? Pink is what? A blend of red and white? It's kind of like I'm showing you red and white and saying the true colors has maybe pink. It's somewhere in between. It's hard to draw pink. Let's move on from this though. In the end, we need to find the true geometry. You can actually get it from either one of these. It's the same answer. What's the hybridization of, well, the sulfur is, it's a little bit different. We got d orbitals here. I like this structure because if you stick with this structure, you can stick with hybridization that we've talked about. If you go here, you got to maybe consider d orbitals. Now, you actually always have to consider d orbitals here, but we ain't going to talk about that. So let's just talk about this structure. What hybridization do you expect of the sulfur?
SB2.
3 regions? sp2? Okay, so how's that sulfur going to be spread out? Yes, it's trigonoplanar. That is, you're going to have oxygen, oxygen, and lone pair. And we can sort of put the lone pair like this. Okay, it's going to take a region. That's minus, that's plus. Basically, the difference is because of the lone pair here, and it demands a region, there's not going to be any funny business going on here. Because of that, this angle is bent here. Not like that. There's no lone pair. Because it's bent, sulfur to oxygen, what do we got? Oxygen more electronegative, right? In both cases, yeah, it looks a little bit different. Which SO bond is longer? No, they're both the same. You know why they're the same? Because of resonance. It's something we got to know going forward. They're actually the same. Because, why did I make that single and this double? Could I not have drawn it the other way and made that double? Again, it's a blend. It's really a bond and a half between each. That's resonance. You need to be reading about it. Okay, in the end, we can still get the answer from right here. Do these dipoles cancel?
No.
No. You don't even have to ask if they're equal. They don't cancel. Net dipole, a little bit counterintuitive, but we're going to have straight through here. Because these are going to add up straight down. A little bit counterintuitive because up here near the positive end, it looks like it's actually a lone pair. That's kind of like, really? Electrons being positive area? But that's what we get here. We could further discuss that, right? Get a cup of coffee on Saturday and really dive into this. There's the answer for us here. Polar. It's got a net molecular dipole moment. Okay? You put this in electric field, okay? I don't know physics. I think I took physics at some point. Electric field may be partial positive side, right? Is this right? And then a partial negative side. And you put this compound in it, guess what? It's going to experience a torque. It'll be moved by the field. Why? Because this positive end is going to be attracted to the negative. All right? And after you talk to physicists, tell me what I was wrong about. I think the torque. All right? These are consequences of polarity. All right? We don't just do this for fun. We didn't say, okay, so what does a polar molecule do? What are the consequences? What can we go do in physics with it? you know? How can you use a polar molecule to conduct electricity, to serve as a capacitor or anything? All right, carbon tetrachloride it's called. It's carbon with 4 chlorines. Let's see. Looks like those should all cancel, right? Well, that's not the right geometry. These are actually like this, right? Right, tetrahedral, twin the plane, went forward, went back. Do they still cancel?
Yeah.
They actually still cancel. We can consider these all chlorines coming off. Every chlorine is going to be pulling, okay? Right? Look at it like this. These 3 would each be pulling up, not straight up. That one pulling this way, and this way. 3 going that way, 1 coming straight down. Well, if you consider vector summation, this 1 straight down is going to cancel these 3, not going straight up, but they're going like this. Okay? They actually do cancel. I really can't see it here as well because it's really the 3D structure. All right? Anytime you have a tetrahedral carbon with 4 things, it's always going to be polar. All right? They're always going to cancel in here. Again, vector summation, which I think you do in physics. All right? Except in physics, you're probably calling it a force. Does the force cancel or something? But what about carbon chloroform, it's called? It's a common name.
Polar.
Maybe let's change the H to green. Usually I'll have H's be black and some like chlorine green, but let's just do it here. Like this, all right? A model is better to have in your hand. Board sometimes a little cumbersome, although you need to be able to draw things on your paper, all right? But I'm not going to take the time here. Here we go. Chlorine, this. Is this CH canceling that?
No.
When we said CH, there is no dipole. Ignore it. Got 3 chlorines pulling up. What's the direction of the net molecular dipole moment?
Towards the.
Right up through here. Because these 3 around sort of, I reckon, equator a little bit, sum up to give 1 straight up through here. How could we possibly show that if I actually... well, let's get a tetrahedral on the board. Chlorine, 1 forward and 1 back. Yeah, that's going to be hard. We're going to have to find the right way to draw it to show it. What if I put the H straight up? Would that help? This is also a little bit misleading. Looks like that's going up. In real life, H straight up. Like that. This chlorine is actually a little bit lower, and these 2 are right behind each other. Right behind each other. Yeah? So if this was on the board like this, the net dipole would be coming straight down. It's coming straight down here. And you got to imagine that these 3 were sort of around this and going down. Okay? So between your paper and maybe a handheld model, you rationalize, you see this better. So yeah. So you got a positive area up here and a negative area down here through your summation. Dichloromethane. This has a common name. Carbon tetrachloride, you don't need to know these, but you can see how they match with your nomenclature. Sometimes these names may be a little bit different from standard IUPAC. Dichloromethane. CH4 would be methane, we put 2 chlorines on it instead of H. It's dichloromethane. Okay? Basically, now we got 2 H's. I know you can't change that quickly, but let's look at it. So H's, let's look at the chlorines, okay? Ignore this here, you got 2 chlorines. Are they canceling each other? No, one's up this way, one's up that way. That's going to sum up to one up straight in the middle. Okay? So again, it's polar, it's polar, polar. Okay. These 2 are polar chlorinated solvents. Carbon tet, it's called, is nonpolar. Okay. You know, we can stand here and talk for 30 minutes about the nuances here, but with everything we do, we have to move on. It's up to you to dig in deeper, satisfy that you understand it, and ask questions, etc. Read your book, you see a little bit different presentation of stuff. That's ultimately how you do well in learning material. Ionics. Okay, well, ionics are obviously polar. Ionics is when you have a huge difference in your electronegativity. For example, sodium and chlorine. It's never covalent, but if it was, the chlorine pools so much that it's not just a dipole, it pulls so much that it just separates. It steals the electrons. Okay? It's like, okay, I'm pulling, but guess what? I'm just going to yank your arm off, and now I've got it over here, and I've got an extra long pair. All right? And I become minus, because I'm so greedy, and I get upset by stealing your electrons. Well, these would be ions, so such as ionic, and that's sort of the extreme polarity. We would not call this a polar covalent bond. It's beyond that. It's now ions. But of course, you should know from Gen Chem that certain things are always ionic, particularly group 1, group 2. And you should know how to show ions and work with ion pairs and salts, etc. Okay, physical properties of functional groups. Or molecules. Molecules are largely consist of functional groups. 2 main things we'll talk about here, boiling point and melting point, and then solubility. Boiling point. Of course, to boil something, you have to overcome all intermolecular attractions. All right? If you all are molecules, same molecule in a flask here, okay? Kind of like your liquids. We'll talk about boiling point. If you're a liquid, you have some interaction. All right? You're rubbing elbows with your neighbor. Okay? Making pinky bonds. Okay? That's what makes you a liquid. Some interaction. If I want to get you to boil, I've got to say, okay, guys, no interaction with your neighbor. No interaction. This will allow you to move into the gaseous state, which is a higher, freer energy, and you will then make you boil. Have to overcome all those interactions. What type of interactions are we talking about? Pinky bonds, rubbing elbows. But in chemistry land, what are these interactions called? And how strong are they? Well, these interactions are called IMFs. Interactions in molecular forces. Intermolecular forces. A pinky bond would be an intermolecular force. So what type of IMFs are possible? All right? Also, we should state this if we haven't already. The more you guys are interacting, the more energy I've got to put in to break those interactions. and to get you to boil. Okay? Higher IMFs is going to equal higher boiling point. What are types of IMFs? They're listed here in order of weaker to stronger. All right? We'll go through these. 1 through 4 discussed below. Number 1, van der Waals attractions. Now in Gen Chem, sometimes you call this maybe London forces or dispersion forces. There's nuances, subtle differences. I call all of this just van der Waals attractions. All right? It's only very minor differences. Okay, here's some examples of how van der Waals attractions come into play. Number one. Look at these examples. If you look at these plain hydrocarbons, that is, they only contain hydrogen and carbon. You could also call these saturated alkanes, although that's a redundant term, right? Because aren't all alkanes saturated? We really don't need to say saturated alkanes. Look at the boiling points. This one is minus 4.2. It's a gas at room temperature. This one's 36. It's a liquid at room temperature. Why is this one higher?
There's more interaction.
What was it?
There's more interactions.
Okay, yes. There's more IMFs? Yes. That's the answer for any of these questions. But you're right, there's more IMFs. That's the first point. But then my question becomes, well, explain. What type of IMFs? More what? Well, you can also say, since we're under number 1, there are probably more van der Waals attractions. I would say, yes, you're right, but we need to further explain. Okay? Yes, there's more van der Waals attractions, there's more IMFs, but that's just statements. What do you mean? Well, there is. It all has to do with surface area here. Okay? You can read this. I'm going to give you the Cliff Notes version. All right? I'm not going to read every little detail here. More surface area. But look at the surface area of this molecule here. I drew that kind of big. Let me do it again and do it sort of tighter here. Surface area, and then surface area here. Which one has more surface area? The longer one, the bigger one. Okay. More surface area. What's on the surface of molecules? Electrons. Because the protons and neutrons are where? In the nucleus. And the electrons are around it. Now the molecule, the surface of a molecule tends to be electrons. Okay? And what are van der Waals, or London forces? What is that?
Temporary dipoles.
It's what?
Temporary dipoles.
The temporary dipole. But how are these temporary dipoles created? Temporary dipoles from the molecules bumping into each other. And you get temporary induced dipoles. You do this in physics. In physics, anybody ever rub a balloon on the wall and it sticks? That's because as it rubs up against, it creates temporary dipoles. Strong enough for attraction to take place. And you've got some molecular attraction going on, and you can see it, the balloon sticking to the wall. Okay? When the electrons rub up against each other, they kind of perturb each other, induce a temporary dipoles, and this leads to interaction. Well, the more surface area you have, the more rubbing up against each other you're going to do and create more temporary dipoles and more IMFs. But it's temporary, it's weak. But even though it's weak, it still has consequence, and it makes this one have a higher boiling point. All right? So if you know what those type of attractions are, really what's new here is more surface area gives you more of that type of thing. All right? But then when we go over here, it looks like a cross, but it's a compound. One carbon in the middle, 4 around. Okay? You can do formula, etc., hybridization. It goes back down, it drops. And it's actually a gas at room temperature, which is usually about 22, 23 degrees. Why did it drop? It's the same number of carbons, 5 carbons, 5 carbons. Where that one was only 3, why did it drop?
Carbons are more bunched together.
It's because it's branched. Okay, and what does the branching do? Because it's branched, it has less surface area than the linear one. Because this carbon here is hidden in the middle. It doesn't contribute to the surface area as much. Take home. Branching does what to boiling point? Lowers the boiling point. Even though you have this, these have the same formula. They're constitutional isomers. We expect lower boiling point because it's branched. Why? Less surface area. Why? Less IMFs. Why? Less rubbing up against each other. You can go on and on and on. They have a deeper explanation. Okay? That was sort of there, okay? More rubbing up against each other. Here we go, number 2 over here. Number 2, which is what? Dipole-dipole. Okay? Look at these. 36. Similar sized compound, much higher, 76. Similar sized compound, those two are much higher than this one. Why? Dipole-dipole. Okay, yes. But why? What does dipole-dipole mean and what is it doing here? Is this compound polar? No, no polarity. How about this compound? Yes, we have a permanent dipole. Because we have a permanent dipole, we can now have dipole-dipole interaction. Permanent though. And the positive, partial negative of the oxygen can sort of interact by physics. And I think in physics you probably call it Coulombic attraction more, use the word Coulombic, just charge attraction. And we attract together, and we show that with sort of a dash sort of IMF. The minus sort of interacting or having a non-covalent interaction. And IMF is also called a non-covalent interaction. We're not making a covalent bond here. You can envision all these molecules now, okay? Your positive end sort of holding hands with her negative end. Good at Coulombic attraction. The difference here, though, this is permanent dipoles. Up here, that was fleeting, temporary. From molecules bumping into each other. Because those molecules up there have no dipole. The bumping in leads to temporary, partial, weak dipole. This is a stronger thing because it's permanent. All right? That's why it's higher. That's how we explain this. What about this one? It's also higher. Look at the T on the end. They have very similar surface area, but this one has a permanent dipole, right? Because of the carbon-chlorine bond. So we can envision the partial negative of one molecule holding hands with the partial negative, partial positive of another. We call this dipole-dipole interaction. All right? So does the trend make sense here? We're looking at examples and understanding the trends. Over here, I think it's number 3. I think 3 maybe got cut off up there. This alcohol has a significantly higher boiling point than this alkyl chloride. Why? They both have permanent dipoles. You can maybe say this one actually has 2, the OH and the CO. Okay. They're both polar. The previous example, the two on the right, were polar. That's why they had partial minus and partial plus. Polar molecules can interact better because they have two opposite ends that can interact. Both of these are polar, but why is this one so much higher? The answer is hydrogen bonding. Hydrogen bonding is just a special type of dipole-dipole. It's a special type of number 2. It gets its own name because it's particularly strong. Whenever you have an H that's on an O inner F, anytime you have an H is on an O inner F, you get a particularly strong dipole. Okay? So all these guys are particularly partial negative. But it's very strong. That's really not the important end over here. The important end is the partial plus on the hydrogen. It's a significant partial plus because those guys are so electronegative compared to a hydrogen. And if you have that, the lone pair that's on an O inner F will really coordinate and make a non-covalent interaction to that H. All right? And that's what you've got going on here. And we can show that so-called hydrogen bonding network like this. Multiple molecules of the alcohol. We've got the H here, very partial positive because it's bonded to that oxygen. Then the lone pair of another molecule on the oxygen can form an IMF to that. And that's called a hydrogen bond. And then you can have a hydrogen bond between like this oxygen and the H is on this molecule, etc. And we're showing the IMF with the dashed line, a non-covalent interaction. Now in this scenario, the H, or the molecule with the H, here, is called the hydrogen bond donor. And the atom with the lone pair is called the acceptor. Hydrogen bond acceptor. So those are important terms. So when you look at these molecules, you have to ask yourself, can this compound hydrogen bond to itself? What do you need to hydrogen bond?
Oxygen, nitrogen.
You need an acceptor and a donor. That's the terminology. Yes, yes. You need an acceptor and a donor, right? What do you need to make Velcro work? 2 pieces. One of them is going to be fuzzier, and one of them is going to have the more harder loopy. Stick together. What if you got just 2 fuzzy pieces? No. If you got 2 donors, they ain't going to do anything. You got donor and acceptor, right? Okay. Can you envision this molecule doing intermolecular attraction by hydrogen bonding? Yes, I can envision the oxygen acting as a hydrogen bond acceptor, and the H of another molecule acting as a donor, and there's coordinating like I showed you in the little diagram. Right? Can this molecule hydrogen bond to itself? Does it have an H bond acceptor? Does it have a donor? It don't have neither. It can't hydrogen bond. It can't do this very strong IMF that gets its own name. Because of hydrogen bonding, which is a stronger IMF, this one has a higher boiling point. Hydrogen bonding explains a lot because it's a very common and very strong IMF. Okay, again, I'm not going to read everything to you. The story is here, the story is in your book, etc., etc. I'm giving you the highlights. Other questions, though? Applications, questions, using this idea. Can't hydrogen bond to itself. It does have dipole-dipole. it doesn't have the stronger type called hydrogen bond. Question, can this compound, which is an ether, can it H bond to itself?
No.
If your answer is yes, then you should be able to show the interaction, but guess what? You can't show it because all I see in this molecule is a what? All I see is an H bond acceptor. You've got an acceptor, here's another molecule, you have an acceptor. It's too bad because two acceptors don't coordinate. No, it cannot. But let me ask you this question. Can this molecule hydrogen bond to water?
Yes.
Yes. You put this in water, then these electrons can make a hydrogen bond to this H, because this H is on an oxygen inner F. All right, so it's partial positive. And these are electrons. Electrons have what charge? Negative. So I mean, you can call that partial negative, depending on how you consider a formal charge. But electrons are negative. Yes, it can hydrogen bond to water. It can hydrogen bond to a variety of solvents. As long as the solvent has a hydrogen bond donor. And just a miscellaneous point, if a solvent has a hydrogen bond donor, we usually call that type of solvent a protic solvent. You hear the term protic solvent because it has a hydrogen bond donor. We can ask questions like this. How many H-bond acceptors and donors does the antidepressant Effexor here have? How many acceptors?
3.
How many acceptors? Somebody says 3. Anybody else? Anybody else? Nobody says 5? Nobody says 5? Here's the question. 2 lone pairs, could each one be hydrogen bonding? You know, this is something else. If so, then do we count that as 2? It can't, only, it's got 2 lone pairs. Can each one participate in hydrogen bonding?
Yeah, but isn't it just one atom?
I agree it's one atom, but when I said acceptor, is this, are we talking about lone pairs or are we talking about atoms? Because if I'm doing this, I'm showing 2 different hydrogen bonds there. Shouldn't that take 2 different acceptors? What I'm getting at is the question is not clear. The question is not clear. I don't know what the best answer is. Is it 3 or 5? Does it matter? Do we understand what's going on? This weekend somebody asked you to tell you how many are in here. I would say, well, do you want me to tell you it's based on the atoms or based on the pairs? Or let's clarify the question. How many donors are present? 1. The H over there that's on the oxygen. There's H's here. But that H ain't on an O inner F. It's on a carbon. And a CH is nonpolar. Question.
So back to the acceptor part, so if we have a question like this on the test, would you specify if we need to base it off the atom or the lone pair?
Yeah, I might be specified. Because here I told you that I don't know. Yeah. Okay. Consequences of hydrogen bonding. Look at these 2 constitutional isomers. This one has a much higher boiling point. It's a gas at room temperature, which means it has much lower IMFs, right? Why does this have higher IMFs? Explain.
Hydrogen bond.
Hydrogen bond. Can this one hydrogen bond to itself? No. Here I see an acceptor and a donor that I could envision forming a non-covalent interaction. How about down here? Liquid, gas, even though they have the same formula. Give me 2 reasons this one's higher.
As a donor and an acceptor.
It can hydrogen bond. What's another reason this is higher? Somebody said it?
Yeah, more surface area. 'cause-
More surface area. Now, that's a minor feature, but still it's a reason. Hydrogen bonding is the major effect, right? It also has more surface area. How about down here? Water 100 degrees. H2S, much, much less. Why?
No hydrogen bonding.
And bonding. See, that's, the H is not on an O. The dipole here is weaker. This does have dipole-dipole interactions, but it ain't as strong enough that we get to call it hydrogen bonding. And we see the consequence. What about C with H's? This is O with H's, S with C with H's. That's even lower. It has almost no intermolecular attraction except for what? Except for van der Waals, but it's so small that even that is tremendously weak. That's why the boiling point is negative 162. Basically no IMFs at all. Down here, antifreeze, which is that simple molecule. Butane, very similar size. Why is this 200 degrees higher? You see it? Why does DNA line up the way it does?
Hydrogen bonding.
Why does DNA line up the way it does? Uh-huh. You see? You see? Now they're not showing the lone pairs here. I probably have a lone pair if you're going to show the IMF. Okay? And the AT and GC, because they particularly line up well. You learn these in biology, right? These base pairs, GC, because they can line up with 3 hydrogen bonds here. AT only has 2 hydrogen bonds possible. How could you do a third here? What would you change about this molecule if you want to create a third if you were designing DNA? What do you want to have over here maybe in this region?
Another
A what?
another oxygen.
Whoa, really?
Or an OH.
First off, we can't have bond. This is going to be hydrogen bonding?
No.
No, you got a what over here? Acceptor? What do you want over here, maybe? Yeah, maybe coming off here, maybe an OH, right? And you could maybe design something. Many applications of hydrogen bonding. Let me pull one out, because I know it'll rock your world. Bulletproof vest. Kevlar, ever heard of it? It's a polymer of this molecule, repeating. And the polymer molecules exist like this. Real close. Strong interaction between each polymer molecule. How?
Hydrogen bonding.
Hydrogen bonding. Strong enough to stop a bullet. Keeps those molecules connected, won't let anything. Technology. It's amazing with chemistry how you take it from the flask to the technology. Right? Okay. Now, the fourth would be ionic attraction. This is even stronger than hydrogen bonding. But it involves ions, which tend to be a little bit unique. I mean, not everything is ionic. But when you do have ions, you got strong attraction because now you have not just partial dipole charges, partial charges, you now actually have formal charges. And these formal charges form even stronger Coulombic attraction. And that's going to make these even more difficult to boil. For example, ethanol has a boiling point of 78, but if you make this ionic on the end, make the sodium salt, this molecule, these molecules together have a boiling point of greater than 500 because it's so ionic. And consider another molecule. This minus is connected to this sodium, but it's also very connected or a bond into an IMFing or whatever you want to call it, to another sodium. All these ions are just clustered together, and in Gen Chem you talk about like a unit cell or something for ions. Okay. They're all masses of charges here, and it's hard to get these to boil. All right? Let's look at melting point. Similar idea, except you're going from solid to liquid when you melt. Now in the solid state, you'd have even stronger IMFs. In the liquid state, you'd have IMFs, but they're not so strong, and so you can still kind of move around a little bit. Solid, though, is like fixed, strong IMFs. All right? Even stronger. But it's the same point. You still have to overcome existing IMFs to go from solid to liquid. Question. One of these here, what have we got here? A tertiary amide and a primary amide. Okay? They're not constitutional isomers. One has a melting point of 126, 144. Which is which? Which would have the higher melting point?
The second one,
Why the second one?
because it has less intermolecular forces. The IMFs are weaker in that one.
No, weaker would make lower boiling point melting point. Higher melting point means it has more attraction. You got to put more energy in to break the existing attraction to go to liquid. Why the one on the left? This one can hydrogen bond to itself, to another molecule. Can the one on the right hydrogen bond to another molecule? No, I see acceptors, but the other molecule down here, where's the donor? It has none, so this cannot do an IMF to another molecule. This one can, because I see an acceptor, and then I can have another molecule. There's a benzene ring, that's quick for benzene ring. I could draw this over here, and put this H here, and then look at here. There you go. I can show an IMF between two different molecules. That's going to make that one have a higher melting point relative to the other one. You can't do that with the other.
So for the molecules, higher intermolecular forces is a higher boiling point and a higher melting point.
Yes. Solubility. Which is what we're talking about in lab. I want to see if something works here real quick. While I'm doing this, any questions about melting point, boiling point? Okay, guys, let's look at solubility. We can start with the old adage, like dissolves like. A compound will dissolve best in a solvent that has similar IMFs. Another way to say that is a solvent with which the compound, which we call solute, is able to have some type of IMF with the solvent. And ultimately, if they have similar IMF possibilities, then they will be able to do the IMF. We'll see examples of what that means. It can boil down to like dissolves like. Question, which amide above would be most soluble in water? Which one would be most soluble in water? To be soluble, the molecule has to associate with the solvent, have good interaction, good IMFs with it. The question is really, which one of these will have the best IMFs with water?
The first one is hydrogen bonding.
This one. Why?
Hydrogen bonding.
Hydrogen bonding, because if we had water here, what type of interaction could we show? Well, I could show, let's draw these H's out. I could show a hydrogen bond between this oxygen and that H. It's a good association of IMF. What else could I show? I could show, again, another water molecule, hydrogen bonding to that H, oxygen to that H. What else might we show? I'd show the H of water, hydrogen bonding to the O there. So lots of hydrogen bonding. Can you show any hydrogen bonding for the one on the right?
Yes.
Yeah, you can. I mean, over here we could show this. Acceptor donor, hydrogen bonding. They can hydrogen bond to water. But what's the answer here? What do you see the difference?
There's more.
This one can hydrogen bond more. I can, okay? I didn't show, I can do that as over here as well. The difference is, here you have, ultimately, more acceptors and donors there, you got more IMFs going on and more stickiness. Okay? We're just maybe making one attraction. By the way, hydrogen bond is pretty strong, so it's not a pinky bond, but typically it's like a good attraction with a hydrogen bond. But over here, we're doing like this. All right? We got 3 hydrogen bonds going on over here. That's going to be a better solvent-solute interaction, more solubility. Okay? This one should be more soluble. But that's a relative question. Is this going to be soluble in water?
No.
That's an absolute question. It will be more soluble than that. This is not actually soluble in water, at least not at room temperature. Why not?
The benzene one.
Because it's got a lot of non-polar part, which water doesn't like. So, important here, relative questions, comparisons are easier than absolute questions. This is more soluble in water, I guarantee you, I bet you a steak dinner, than that, relative comparison. But is it soluble in water? It's harder to answer. Usually we'll do relative comparisons. Okay, like dissolves like. Basically, I would say that this is more polar, because hydrogen bonding is a polar phenomenon. This has more polarity, hydrogen bonding. Water is very polar, so that's kind of the like dissolves like. This, on the other hand, has these carbon groups, which sort of decrease the polarity, because the dipole between N and carbon is not as strong as the dipole between N and H. So I would roughly call this to be sort of more polar. Hydrocarbon is opposite of polar. Okay. There'll be more examples. The lab gets at a lot of this, but what we just talked about there is the general overview. There was another question down there, right? In hexane, which one would be more soluble in hexane, which is just, okay, you gotta watch nomenclature. Just a plain, straight hexane, hydrocarbon. Why the one on the right? Because it's less polar. Yes. What's going on here? We're talking about soluble, so we're starting with the original. These are solids. And in the solid form, these molecules are triple bonded. They're like this. Okay? Lots of hydrogen bonding. Here comes hexane. Why would hexane be able to disrupt all this hydrogen bonding? This molecule is not going to want to let go from the hydrogen bonding and interact with hexane. Why? There's no reason to. On the other hand, this one doesn't have as much. It's only holding one hand. Hexane is more easy to get in there and disrupt it and solubilize it. So that's again like dissolving like. Simple adage. Less polar is going to like the more or less polar solid. Okay? What are some examples of solvents? I show some here, some very common ones. I distinguish, first off, you got water, and then you got organic solvents. All right? But organic solvents, you have, I've distinguished between polar and non-polar. So polar ones, acetone, we wash our glassware with, ethanol, DMSO, you can look that name up, DMF, acetic acid, can't be used as a solvent. These are just a couple. You'll see others in lab. These are all polar because if you look for a permanent molecular dipole, you will find one here in each of these. Over here, I call these nonpolar. Now, that's a little bit partially confusing. Because this diethyl ether, it's actually a polar molecule. If you look at it. Because the O-carbon dipoles are not going to cancel. So why am I calling it a nonpolar solvent? It's because a common distinguishing feature here is I'm saying that if it's soluble in water, I'm going to call it polar. These are not soluble in water. And so in general we can say they're nonpolar. That's a general description. You've got to see that. The only one over here that's actually nonpolar is hexane. And maybe toluene. These are certainly polar molecules. The problem is they're not polar enough to make them soluble in water. Because it's got this hydrocarbon portion. Okay? Yes, these can hydrogen bond to water. They're still just not soluble in water. So that's how I'm distinguishing them. These solvents that are not soluble in water are good for extractions, where you want two layers. You want an aqueous layer and then an organic solvent layer. You can do an extraction with hexane or ethyl acetate. You cannot do an extraction with acetone, because it will just mix with the water and you will only have one layer. Okay, you don't need to learn or memorize all these solvents, but you do need to refer back to this page occasionally. And probably a month from now, or in our case, 2 weeks from now, I'll say, DMA, you know, it was on that list I showed you back in the physical properties. Water is called the universal solvent, but they were lying to you because they didn't know about organic chemistry. Water only dissolves a small amount of organics. Sugar, a nice neutral organic. But guess what? Usually you have to heat the water to dissolve the sugar. In the recrystallization demo that you're going to watch next week, I demo with water. But I have to heat it to get my organic compound to dissolve. Ionics, much more soluble in water. And our starting point for ionics is, we say ionics have good solubility in water. And with acid-base chemistry, we say if we can make it become ionic, then it will actually prefer the water. Ionics prefer water, good solvent for water. Yes. But there are exceptions to that. And some that are very, very important for medicine. For example, calcium oxalate. It's an ionic. It's actually got, it's doubly ionic, sort of. It's got an ion pair here and here. Although the ion is a divalent, it's calcium 2 plus to go with 2 minuses. Okay? You might say it's ionic, it should be soluble in water. Well, it's actually not. Or not that soluble. And calcium oxalate forms kidney stone. If you get too much of this, it'll form solids in your kidneys. And then you'll have problems. Now you got a lot of water around in your kidneys. Usually all that water dissolves ions, but this is an example of an ion or a salt that will form a solid in water. It doesn't have solubility in water. Another example is sodium urate. It's ionic, but the solubility in water is not great. And it will precipitate in your joints, and that's a condition called gout. Okay? You get this solid that's forming because it's no longer soluble. Okay? So organic solvents are good for organic. You can read that there. Then extraction. We'll look at this a little bit later. The idea of an extraction is very important. 2 different solvents. Very often you're using an acid or a base as the aqueous portion. And we can separate compounds. We need to do a little bit of acid-base chemistry first to really understand this. Let's see what else is here before we move on. Crestor. This shows Crestor binding to the enzyme, the HMG-CoA reductase enzyme, which it binds to and inhibits, and thus limits the amount of cholesterol your body makes. How do drugs act? Typically they bind to enzymes. How do they bind to enzymes? When we say bind, what does that mean?
Make bonds.
Bind covalently or non-covalently? Typically non-covalently. How can something bond non-covalently? Hydrogen bonding, or dipole-dipole, or van der Waals, or what's another one? Could even be some ionic attraction, which would be an example of non-covalent binding. Actually, there are some drugs that actually covalently bind to enzymes. Sometimes those are called, I think, suicide inhibitors. Because once it binds covalently, it's like stuck. And then that's something that maybe like in cancer where you don't want to worry about so much selectivity. Typically, drugs interact by non-covalent interactions. How is Crestor interacting with this enzyme? Enzymes usually have a particular region. And this is the region shown. Typically, amino acids make up the enzyme. What type of interactions do you see? Yes, probably. We've got to be careful. I don't know who's drawing these things out there, but I don't know if they had too much chemistry. So you got to be on the lookout for some of this. Like here, I mean, come on. Can't you put lone pairs if you're going to show some hydrogen bonding?
Is the OH binding to another?
Where you see it? Is it?
Like not, yeah, like
Where?
not that one, not the next line, but that one.
Here?
No, one over to the left, that one, like that line.
Yeah, what is this? Oxygen to oxygen?
Yeah.
I don't know.
Oxygen to
I mean, come on. It's like, okay, let's get a little, let's throw the H out here, and that can hydrogen bond to that. And then let's put a lone pair here, and then maybe an H, and this can hydrogen bond to here. Yes, please grade this, okay? All right, see what's going on here. For example, I don't know what's going on here. I mean, I kind of do, but it ain't shown right. Right? You see? Let's look at some of this. What is this here? You could call this hydrogen bonding, because you got it, I mean, oxygen, even though it's an anion, let's put a good charge here, I mean, come on. But this is an anion and that's a cation, so this is like ionic attraction. I mean, these are formal charges. Or you could show hydrogen bonding there. What else is going on here? I mean, it's the same thing. O to O, I mean, come on.
The OH to HO up at the top, over to the left, down, right, no, right?
The OH to.
Yeah.
Looks okay. What about here though? What is this? First off, these are amino acids. Have you learned amino acids? Okay, some side chains have just hydrocarbon. Like off of valine, I think it's probably just maybe a nice butyl group. Okay, coming off the amino acid. Just hydrocarbon. Well, what is this here? Part of the drug. It's just hydrocarbon. Can these interact in any way?
Yeah,
How?
van der Waals.
Yeah. Just a weak van der Waals. They're calling it hydrophobic bonds. What does hydrophobic mean to you?
Not like one.
Doesn't like water. Yeah. That's not going to like water. He's not going to like water. Can these groups still bond? Yeah. Okay. Is it a covalent bond? No, it's a non-covalent. Okay? You got to be careful with this terminology. All right? Now, a lot of this terminology can confuse beginning students a little bit unless you are willing to ask questions and be open to, okay, what do they exactly mean here? Because I thought this, and I'd say, you're exactly right, this is just a nebulous term. But this is realities of science. And a lot of this stuff, as you go along, you just ultimately, after 5 or 10 years, you just comes to working language. All right? Anybody ever heard of Crestor? I'm sure if you watch TV, you've heard of it. What's at the bottom? A soap. Okay? When you take a bath, do you use water or acetone? Water, okay? But on your skin, usually oils. Or dirt, but dirt you usually wash off mechanically. A lot of times though, you clean off oils out of your hair. Okay, those oils are not water soluble. So what do you use? Soap. What is a soap? A soap is like an arbitrator. Okay, a soap is like this. It's got a polar end, and then it's got a non-polar end. And it helps bring the two together, okay? This is like hydrogen bonding to water, H's. And then this is interacting with the oils. Some hydrophobic bonds, van der Waals attraction. And so it's like, okay, I'm bringing the water here and the oil, and we all make a, come together. And also, you can get stuff like this. It's known that the soap sort of surrounds the grease molecule, the oil, with these hydrophobic ends, hydrocarbon ends, and then leaving the surface of this, the polar head groups, that water can interact with. So it helps solubilize the oils and dissolve them. So there's lots of applications here. Drugs. Take a look at that, the difference in these two, the questions over there. We'll move ahead here a little bit. Also take a look at this. This is one of my newer handouts. Agricultural fields. Anybody ever spray for weeds? Okay, you're very often a mixture, but it may be dicamba may be in there, or 2,4-D. But you can read about this. There's potential for runoff and contamination and et cetera. This is an application of some of the IMFs, okay? We don't always have time to go into all these. To me, this is what makes it all interesting, though, the applications. Why are we learning this stuff? So you can go out and work for an ag company and do chemistry research on pesticides. These are the type of issues they're dealing with. And creating new technology and making new compounds. Then on the back, take a look at that. We'll maybe look at two of these things another day after we've looked at it a little bit. So this afternoon, tomorrow, solubility lab to put some of these things into practice and to learn a few other things and start working with solvents. Any questions about that physical properties handout? We need to be thinking about a quiz. We have a quiz. I'll have to think about it maybe tomorrow. Or maybe on, what's next day? Today's Wednesday? Or maybe Friday, yeah. Very well could be tomorrow, though. Our first test is next Wednesday. How are we doing with IR? Any questions about IR? The problems in the workbook? That's the type of problem you'll see on the test. Question?
Question about the quiz, will it cover the nomenclature as well?
No.
Oh, yeah, and then for the nomenclature, is it just the first video? Because I know that you have 3 already got playlists. You have one that says,
The other one should say test 2.
yeah, and then there's another one, I don't think it's specified which test, or is that the last one?
Okay, it definitely says 2.
Okay.
Yeah. There's only one nomenclature video for each test. 3 tests, and each test there'll be a nomenclature video.
Will IR be on quiz?
Not sure. It could be, should be. Might depend on the day. If we do a quiz tomorrow, then maybe not. I'll give you one more day, then maybe I would include it. In any event, we're summer here, you're going to be on it. Okay, next handout should be acid base. I think that's a white one. Okay, the lab today and tomorrow also includes an acid base using the sodium hydroxide and the sulfuric acid. The intro to the lab discusses this. We'll be going over this as well in this handout. There's other acid base. Here's some types of questions that you may see. Nice question there, drug application. The acid-base mechanism. Hugely important. Acid-base is a reaction. Just about all reactions we do will have a mechanism where you show the movement of electrons using arrows. Mechanism arrows, sometimes called curved arrow formalism. Show the reaction, that we understand what's going on. Okay, any acid-base reaction is going to have the same exact mechanism. We're talking about Bronsted-Lowry traditional acid-base with a proton. Okay? We have got to work to understand mechanism arrows. We've already done it a little bit. When I said WDAM, we just move the electrons to make a bond. Okay? We've already started doing that. One of the most important things in this course is learning reaction mechanisms. Because when we do reactions, we don't just memorize products. Just like in math. You memorize all the answers. What's 25 times 34? Quick. You didn't memorize that one? If I gave you 1 minute, could you tell me the answer? Certainly you could, because you know a mechanism for arriving to the answer. So now listen to this. Understand what's going on, then you can just predict. Deal with anything. If all you do is rely on memorization, you're going to quickly run out of room and it's going to be, well, I didn't memorize that one, sorry. And I don't know how to deal with this reaction. Okay. Starting with the acid-base mechanism is a great place to start. It's only one mechanism. Test 2 will have many mechanisms. The fundamentals are there, core basic things that you can do. Okay, in any acid-base reaction, you're going to have an acid and a base. This will be the base, and it's going to have a basic atom, typically a lone pair. The lone pair reacts with the proton, the hydrogen. The other molecule is going to have the hydrogen. It's going to be called the acid. And it's going to be bonded to something. I call that Z because there ain't no Z up there. It's just generic. Now, Gen Chem, you'll learn that the acid donates the proton. Is that right? Is that right? Acids donate the proton? Terrible. Don't consider it like that. They don't donate anything. It's like when someone steals your bicycle, it says, well, you donated your bicycle to the thief. No, I did not. The thief took my bicycle. The base takes the H. That's mechanism. Think that way and you're going to be better with your mechanism. And the mechanism, the lone pair, and also I'll circle the lone pair because that's what we're kind of doing. This thing goes and bonds to the H. The arrow is going to make a bond to it. Simple as that. Showing I'm making a bond to the H. These electrons have to go away from the H because H can't make two bonds. So these electrons move, what does that arrow mean? They move onto that atom and actually become what? They become a lone pair. But I show this outcome over here. The basic atom is now bonded to an H. You see these two electrons here and that two electron covalent bond? What were they over there? They used to be a lone pair, but now the lone pair is bonded to the H. And the H doesn't have any electrons. Because the one that it did have or owned, it got moved to the Z atom as well. And the Z took on a lone pair, as shown by that arrow. There's the lone pair. Okay? And this is the same for any acid-base reaction. What I have not shown here is charges, because charges can vary. Maybe this is an anion, or maybe it's neutral. Maybe this is neutral, or maybe it's a cation. So I didn't show it in my generic scheme. Okay? I explained arrow 1 and arrow 2 here. That's your mechanism. Charges can vary, you know, a little information about charges, but you know how to determine charges, how to recognize them. Again, if it ain't standard bonding, it's probably going to have a charge. All right? Now, based on that right there, you should be able to show the product of this reaction over here, of this drug. You may need additional information because we need to identify the acid and base. What's the acid in this reaction?
Hydrochloric acid.
ACl. That's easy. What's the base in this reaction? What?
Trembo.
I thought someone was going to say the drug. And I would say, yes, you're right, the drug is the base. But what atom of the drug?
The OH.
Not the OH. Okay? That's the type of question we need to learn about and to be able to really figure out. Because we got to identify the basic atom. What is the basic atom of the drug? Okay? Let's get going. You can go back and answer those types of warm-up questions. Here we go. Acid-base chemistry. Everything up here is reviewed. You know Ka. You know we don't use Ka. Instead, we use pKa. pKa equals negative log of Ka. Stronger acid will have thus a lower Ka. pKa. Stronger acid, lower pKa. Everything up there is a review. Very important. You should pull out your Gen Chem book and have that with you. I also showed an acid-base mechanism, which is the exact we just looked at. Okay? Now, a lot of times you'll just say ionization of the acid to make H+. That's not reality. H+ cannot exist by itself, even though we show it like that a lot of times. To have a reaction, you got to have a base. And so let's include water. Include water, water takes the H. And you form hydronium ion plus the ion. So H+ always exists with something like water. Okay, if it's an aqueous acid, it's okay. You got to have water acting as a base or something. But we will a lot of times just say H+. Okay, let's look at examples of stronger acids having lower pKa's. HCl, strong acid, you learned that in Gen Chem. Have pKa, it varies in textbooks from, I say, like -7. Very low pKa, strong acid, is completely ionized in water. Definition of a strong acid. Acetic acid. This hydrogen is acidic, pKa of about 4. Not as strong as HCl. Considered a weak acid. You put it in water, it only partially ionizes. That is, you have an equilibrium, a dynamic equilibrium where some is ionized and some is not. And that equilibrium is described by the pKa of 4. We can go to an alcohol. This H has a pKa of 16. It's less acidic. Alcohols are considered neutral, or that's considered acidic. When do you start calling something an acid? Traditionally, you don't call it an acid until the pKa gets below blood pH, which is about what? About 7, 8, depending on the, okay? If the pKa gets below that, then we typically start calling it an acid. So acetic acid, but ethanol at 16, we don't call an acid. All right? Anything with an H can act as an acid if you got to start with a base, but we never call that an acid. Just like water. Do you call water an acid? No, you don't call it an acid. Can it act as an acid?
Yes.
Certainly. But we just don't call it an acid. Okay? Because the pKa is not below blood pH. Okay? That's just sort of historical terminology. Okay. And then just like hydrocarbon, these H's here, pKa greater than 40. Certainly not hardly acidic at all. The least acidic hydrogens in organic chemistry. But why? Why is this more acidic? That's what we need to look at. And the why is based on these four things. Okay? And let's look at each of these four. Sort of like we looked at the four things of IMFs. One is electronegativity and size of the atom grouped together. Water versus HF. Which is a stronger acid? HF, but you maybe just sort of know that from memorization. But why? Why is HF a stronger acid?
Fluorine is more electronegative.
Okay, you may be able to rationalize it. Let's do it here. What we really need to look at, anytime you're considering acidity, you really need to look at the conjugate bases. What's the conjugate base of water? Hydroxide. What's the conjugate base of HF? F minus. Okay? Large number of you probably do not know how to show conjugate bases for any given molecule. You've got to be able to do that to start. But you should have learned that in Gen Chem. If you need a refresher, pull out your Gen Chem book and look at conjugate bases. All right? What we need to do is look at the conjugate bases and compare the stability of them. Which is more stable? We got O minus or F minus. Which is more stable? The answer comes from this. Which one doesn't mind being minus as much?
Fluorine.
Fluorine. Why? More electronegative. Likes being negative. These guys like being negative compared to over here. Which likes being negative more, carbon or boron? Carbon. But not a lot. Nitrogen likes being negative more than oxygen. You see a good bit. These guys are all C minus a lot. Yeah. F minus is more stable. Okay, because it's more electronegative. Thus, HF is more willing to act as an acid and come to F minus. Hey, somebody come take my proton. Okay? Somebody come take my proton, and then maybe ammonia's like, okay, I'll come steal it or take it. I'll come make a bond and then move these over there. Base, this serving as an acid. And when that moves over there, what does this become? F minus. And F minus is like, yeah, now I'm minus, because that's what I want to be. Oxygen, on the other hand, is like, yeah, I can become minus, but I don't love being minus. Not as much as you, F. HF is a stronger acid. I would almost say it's more willing to donate the proton, but then I'm like, no. It's more willing to let the base come steal the proton. Let's say it like that. Okay. Stability of conjugate base. Stability of conjugate base is down here as well. Which is a stronger acid, HCl or HBr? We need to consider the stability of the conjugate base. What's the conjugate basis? Right here. Which is more stable? Based on electronegativity, which one is more stable? Higher to the right. Chlorine likes being minus more, based on electronegativity. But that gives you the wrong answer here. Br minus is actually more stable. Why? Because it's bigger. Periodic trend, we do know these are bigger. And it turns out that because it's bigger, the charge is more spread over the atom. And if we can spread the charge out, it makes it more stable. So in this case, size of the atom is better than the electronegativity argument. Contradictory arguments. Which one wins out in this case? Size of the atom. Size of the atom is most important when you're going straight up and down. Which is more stable, an O minus or S minus? S minus because it's bigger, even though oxygen is more electronegative. Bigger, more spread out, charge more spread out, more diffuse. That's more important. Which is more acidic? HBr or HI? HI, because you'd rather form I minus. Bigger.
So the only time you go to the size of the atom is if you're looking at two elements that are like in a
The only time you want a clear answer. Because if you start going diagonal, it becomes less clear. Still may be important, we might still use the argument, but it would be like your argument is not as definitive. It's going to be very definitive up and down. Those are Jenkin acids. What about organic acids? What's the most acidic H in this compound here? The question is really this. On which atom do we want to form an anion? Because if it acts as an acid, it's going to become an anion if it's beginning neutral. That's really the question. Where's the best place to make an anion? First off, what about a CH? Are those going to be acidic?
No.
And make a C minus? Carbon don't like being minus compared to maybe one of these other guys. So forget about CH. What's the most acidic? Well, let's compare two. Which is more acidic, NH or SH? But that's diagonal. So I'm going to keep it straight up and down or straight across. That'll work better. Even though we can still get the answer. Over here, which is more acidic, SH or OH?
SH.
Yes, you'd rather have an S minus than an O minus. Because S minus would be more stable. But now we're diagonal. I think it's best to do this first. Which is more acidic, OH or NH? OH, because you'd rather have an O minus than an N minus. Because O is more electronegative, clearly. More acidic. More acidic than NH. Now let's compare these two. OH or SH? SH. So it's more acidic than that. So we eliminated them all, and the SH is most acidic. We might could have easily got the answer the other way, but I thought we needed to go this way. Okay? So we can rationalize and by deduction get down it. Yeah, the SH is the most acidic. There. Okay, so that's using electronegativity and size. You got to be careful though when you're using size, the charge has to be on the atom. If the charge ain't on the atom, the size argument doesn't apply. You're like, well, when would I ever do that? Well, probably tomorrow somebody will come by and they'll say, well, guess what? The charge ain't on the atom. And you'll go, oh yeah, that's right. All right? Number 2, inductive effects. Which is more acidic? This compound or this? First off, are we talking CHs or OHs? Yeah, we're really talking about the OHs, because that's the most acidic of each compound. But which OH is most acidic? What's the difference? This one has a fluorine. What do we want to consider? The conjugate basis, right? What do they look like? This. Which is more stable? O minus or O minus?
O minus.
Right. That don't give us the answer. We got to look at something else, right? What's the difference? Fluorine. This is inductive effects. What does the fluorine do?
Electrons towards
The
it.
fluorine is a little greedy little you-know-what. It pulls electrons. Okay? Like tug of war. It's out there pulling. And we can show a dipole. We can actually show sort of a huge dipole because the effect is not only here. These electrons get pulled, but so do those a little bit, so do these a little bit, and all this gets pulled through here. All right, that greedy fluorine. What's out here?
Hydrogen.
No fluorine, nothing pulling. So is this pulling going to stabilize this O or hurt it? It will stabilize it. How do you make a negative more stable?
Get rid
Something with lots of electrons, how do you make it more stable? Pull electrons away from it. Okay, you're negative. How do I make you more stable? What if I give you more electrons? You don't need more electrons. Things ultimately want to be neutral. Even electronegative atoms, neutral is better. Okay? Pull away, that stabilizes it. That makes this more stable, because over here there's nothing pulling. That's more stable, thus which is more acidic? This. Because this is more willing to act as an acid and become that when it acts as an acid. Now importantly, we got to say over here is, this end over here is just plain carbon, hydrocarbon. And plain hydrocarbon actually donates. By the way, we didn't use the term inductive. This fluorine is pulling through this single bond, through that single bond. When you pull through single bonds, okay, over there, I'm fluorine, I pull through this single bond, and I affect you way over there. Through these single bonds, that's called induction, or an inductive effect. Pulling through single bonds. Or pushing or donating through single bonds. That's also inductive. This is called inductive withdrawing. But an sp3 carbon inductively donates. Donates by induction. That's something you just have to know. It's not really intuitive. Why it does this is something you have to hear and know. It's very important, and you will often use that. That plain sp3 carbon donates, right, by induction. So, the fluorine pulling inductively stabilizes this, making this more acidic. Which is more acidic here?
the first
What's the difference? First off, let's make this quick. We're really considering the anions, right? Which anion is more stable? Let me say this, guys. A lot of times we'll do things quick. But usually when we show charges, I want you to always show electrons. Full formal structure when it's charged. If I'm going to show that minus, get rid of the H, really need to show the electrons and make it sort of complete whenever we have a charge. If there's no charge, it's okay to just omit the electrons or okay. Charge, let's make it complete. Always. Okay, which anion is more stable? What's the difference? This one has an extra sp3 carbon. What does it do?
pushes electrons.
It donates inductively. This one doesn't have the extra carbon, so it doesn't have as much extra donation. Is the donation going to help or hurt this anion? Will hurt it. So which is more stable? This one. Thus, which is more acidic as the H compound? This one. This H compound is more willing to act as an acid and become the minus because it's more stable compared to that which has something extra that hurts it. Let me end here, we'll continue here tomorrow, but let me ask you this question about these two here. Look at these two anions. Let's talk about bases for a minute. Which one of those would be the strongest base? The other one. Why? What's your rationalization? Yeah, it's less stable, but why does that make it a stronger base? Stronger bases, that means it's more eager to go take an H. And when it takes an H, what does this become? Charge? Goes back to neutral. Which one of these is more eager to get back to neutral? This one. It doesn't like being minus because it's got this over here pushing. It's like, I'm too much minus. I don't like this at all. I need to go back to, where's a proton? I gotta have a proton. Boom, I take a proton. I act as a base. Okay? So understanding allows you to make the same argument over there. Bases want to take H's. Which one wants to take the H? That one. Okay, guys. We'll continue on with this one. This handout, a lot here though. Please be looking ahead, reading. We'll see more resonance.